Good morning, everyone. Today we're continuing with chapter 8 by doing 8.6a. So we are writing and graphing exponential and decay functions. So what we got to do first is tell whether the table represents an exponential function. If so, write a rule for that function. So what we need to do first is look at how these numbers are changing. They're changing by adding 1 on the top, which is fine. We want them to be adding something on the top. On the bottom, they need to be multiplying by the same thing every time. So on this one, it looks like we're multiplying by 3 every time. So if we're multiplying by 3 every time, then we know that this is an exponential function. So we got to write a rule then. We always start with our y. So we have y equals, then we go to our a. The value of a is when x equals 0. So x equals 0 is 1/3. So 1 over 3. And b is what it's being multiplied by. Well, it's being multiplied by 3. We have 3 to the x power. Over here, we are multiplying or adding up by 1, which is good too. We can still add by 1. Now here, it looks like we're dividing, but what we're actually multiplying by is 1/4. We're multiplying by 1/4 the entire time. So what this is going to be is y equals, when x equals 0, y is 1 times 1/4 to the power x. Let's try this one. Graph the function y equals 3/5 to the power x and identify its domain and range. So we know we always want to have a 0 in here. We want to have a couple positive numbers and a couple negative numbers. So I have -2, -1, 0, 1, and 2. So if we put this into our function, 3/5 to the power x, what I'm always going to start with is 3/5 to the power 0x, or to the power 0, which is going to give me 1. So for 0, our y is going to be 1. Then we have 3/5 to the power 1, and 3/5 to the power 1 is really just 1/3. So I'm going to write that as a decimal, and I'm going to say 0.6. Then maybe 3/5 squared. 3/5 to the power 2 gives me 0.36. Now if I do 3/5 to the -1 power, I get 1.67, and 3/5 to the -2 power gives me 2.78. So if we start here at 0 we're at 1. So we'll go to 1 there. At 1 we're at 0.6. So 1 would be here, 0.6 would be about there. At 2 we're at 0.36, so a little bit less than 0.6. -1, we're at 1.67. And -2, 2.78. So what we have is a decay function. because if we go from left to right, it's going down, it's decaying. Now, our domain are our x numbers. Now, we could do anything for our x numbers, so our domain is all real numbers. The range, though, is our y values. Now, our y values look like they never go negative. All of these are positive. So our range is all positive real numbers. So now we need to tell whether these represent an exponential function. If so, write a rule for that function. Top ones are going up by 1 for these. So that's good. We want that. The bottom looks like it's being divided by 10. What it's actually being is multiplied. Oh, not added. It's being multiplied by 1/10. So our rule for this one then would be y equals 1 times 1/10 to the power x. Here we have adding 1. On the bottom, though, looks a little strange. If we are multiplying, let me put this in my calculator quick. Here we divided by 1.11. So let's see if that's true for this one. If I do 10/9 divided by 1, I get 1.11. So what we're multiplying by here is we're actually multiplying by, excuse me a second. We are multiplying, okay, so I got it. So y equals, we start here at 1 times, and then what we're multiplying by is 1/10. We're actually, multiplying by 9/10. Multiplying by 9/10. Here, this one, we're just adding 2 onto every one of these. So this is actually not an exponential function. Alright, this one we have 0.4 to the x power. We want 0, 1, 2, -1, -2. If I do 0.4 to the 0 power, we get 1. 0.4 to the 1 power, 0.4. 0.4 squared is 0.16. 0.4 to the -1 power gives us 2.5. And 0.4 to the -2 power gives us 6.25. Now I would just put those in your calculator. I think that is the easiest way to go for these problems. So if we graph these, 0, 1, right there, 1.4, maybe right there, 2.16, negative 1, 2.5 is up here, and negative 2, 6.5, 1, 2, 3, 4, 5, 6.25 gives us right there. So it looks like this is also a decay function. It's going down if we read from left to right. The domain is our x values. We could have wrote anything for our x values, so it's all real numbers. The range, then, well, it looks to me like it does not go down here, so we know we have all positive real numbers. Alright, I want you guys to try this one on your own. It's good practice, so maybe make sure you have a 0, 1, and 2, negative 1, and negative 2 in there. Then put those into your calculator so you can find your exponential function. So here we're talking about exponential decay. So when a quantity decays exponentially, it decreases by the same percent over equal time periods. To find the amount of the quantity left after t time periods, use the following model. So A is the initial amount. We have 1 minus r this time. And we still have t for our time. So r is the decay rate, t is the time period, 1 minus r is the decay factor. Well, how is this different from the growth model? Well, in the growth model, it was 1 plus r. Here in the decay model, it's 1 minus r. So it's different from the growth because this time we're subtracting the rate, not adding it. Alright, this one says, you purchase a cell phone for $125. The value of the cell phone decreases by 20% annually. Identify the initial amount, the decay factor, and the decay rate. Then find the value of the cell phone after 3 years. Well, let's start with the initial amount. Now, the initial amount is the first amount, what you start with. This one says you purchase a cell phone for $125, so the initial amount has to be $125. Then it says find the decay factor. Let's find the decay rate first. The decay rate says it decreases by 20% annually. So it's decreasing by 20%. Now, whenever we write a rate, we want to write it as a decimal. So 20% is actually just 0.2. Now the decay factor, we just have to write 1 minus whatever our decay rate was, and that was 0.2. So if we write this into our equation, we have y equals our initial amount A, 125. Oh, hold on a second here. 125. see if I can delete this here. Alright, let's try that again. 125. There we go. Our decay rate was 1. Our factor was 1 minus 0.2. And it says, what are we going to find this at the time period? Well, we want to find what it is after 3 years, so to the third power. So I'm just going to put this all into my calculator, just the way it is. 125 times 1 minus 0.2 to the third power. What I get is 64. So after 3 years, this cell phone, you bought it for $125. Now it's worth $64. Alright, match the function with its graph. Alright, so first of all, we need to look at if there's anything with a negative. So as I see a negative down here, what this number here, or number 3 is saying, is that I have a negative 1a times 1/2 to the x power. So anything that I multiply by 1/2 to the x power, I have to multiply by negative 1. So anything that I have is going to be negative. So I know that 3 is going to go here with b. Here we are multiplying by 2. We have 2 to the x power. So if I have a whole number, that's going to be a growth function. So a growth function is going to be a here. Then I have finally the 1/2 to the x power. If I have a fraction, that's going to give me a decay function, and the only one that I have left is c, which is a decay function because it's going down